Namaskar students, I am Hiren Kherala from Gyan Manjari Institute of Technology Bhavnagar. We are discussing about sinusoidal steady state analysis. In previous lecture we are discussing about what is sinusoid, what is phasor diagram and all other relevant terms. In this chapter we are going to discuss basically about effective or RMS value of voltage in currents. Now, what is the RMS value or the effective value of voltage in current? So, whenever we are dealing with some kind of voltage source or current source, in that case, generally we are representing the voltage and current in form of RMS value or effective value. Okay, not in the form of peak value or average value or instantaneous value. So that RMS value or effective value that we are going to understand. So the idea of effective value arises the need to measure the effectiveness of sinusoidal voltage or current source in delivering power to a resistive load. So we are taking a load as a resistive in nature, and we are going to find when current source or voltage source is connected to this kind of load, what will be the behavior of the system. Okay, either it can be a current source or voltage source, how the effectiveness of sinusoidal voltage or current source in delivering to the power to the resistive loads, because in case of DC system or AC system, the power to the particular resistive load or any kind of load will be same. Okay, so here we are dealing with sinusoidal voltage and current sources. In case of DC source, we are okay. Let me just give briefly introduction of what is RMS voltage. So the effective value or the RMS value of periodic current is the equivalent DC current that delivers the same average power to the resistor as the periodic current does. So it does mean that whenever we are connecting a resistive load with AC source and with DC source, the average power to the resistor will remain same. Okay, so now let us consider this resistive load we are connecting across, let's say DC voltage source is here. Okay, same we are supplying AC voltage source. Okay, now here we are connecting a switch that we can toggle. Let's say this point is point 1 and this is point 2. Okay, now when this switch is connected to point 1, at first instant we are interested to find the total power absorbed by this resistor R. Okay, so if we want to find that a total power P, so the definition of average power is we have to find the value of power for one period cycle, and one period is nothing but your, for sinusoidal it will be T. Okay, to complete one cycle, that is 0 to T second. So your T and here is your P. So average power is nothing but your power that will required to come in one cycle. Okay, so you just it is the definition of average power, 1 divided by T integration 0 to T P dt. That is what the power absorbed by a resistor in case of a AC circuit. Okay, now here P is equal to V. Now P is nothing but your sinusoidal voltage multiplied by current. Okay, and from Ohm's law we can write V is nothing but IR. V is equal to I multiplied by R. So put this value of IR into this equation, so that will be IR multiplied by I. It will be I square R. So this value is nothing but P is equal to I square R dt. So this is what the average power that absorbed by a resistor in case of a AC circuit. It means when this switch is at this point, number 1. Now we are toggling this switch at point 2. In that case, this circuit will be there, and the total power P in case of DC supply can be given by P is equal to I effective square into R. Now here we have represented the current in terms of effective power. Here we have taken the only I. Okay, now let me come to that point. So in case of a DC circuit, your power will be simply I square R, because your signal voltage input signal is a DC signal. It will look something like this, VDC. Okay, so your time axis, your voltage axis. But in case of resistor, the nature of the signal will be sinusoidal. That is why we have to take the integration of one period, that is 0 to t pdt. But in case of DC circuit, we don't have to worry about sinusoidal nature of the signal, because the value of voltage and current will be same throughout the entire period. Now the absorbed power, that is the average power absorbed by a resistor, will remain same as per our definition, that the effective value of periodic current is the equivalent DC current that delivers the same average power to the resistor as the periodic current does. It means that power in case of AC and power in case of DC will be same. So we can write that P is equal to I effective square is equal to R is equal to nothing but the equation in case of AC circuit, that is 1 divided by T integration 0 to T I square R dt. So we are just put this value into this in this equation, that is 1 divided by T integration 0 to T I square R dt. Okay, so we are saying that the power absorbed by a resistor will remain same in case of DC or in case of AC. Okay, now you can just cancel out both this resistance R. In that case, your final equation will be I effective square is equal to 1 over T integration 0 to T I square into dt, that we have written right here. So from above equation we can observe that now just to find I effectiveness, we are taking under root both the sides. So it will be under root of 1 over T integration 0 to T I square dt. So this value is nothing but your current effective value of current, or the RMS value of current. It means root of mean of square. Okay, so here you can see the square of current. We are finding the mean of that value and we are going to finally take under root of current. Okay, that will give you I effective or I RMS value. Same way you can find for voltage, and it will be also the same. So the effective value of voltage can be found out in similar way, that is V effective is equal to 1 over T integration 0 to T V square dt. Here you in case of power, V that is equal to V into I. We have put V is equal to IR. Here you have to put I is equal to V by R. So that will be V square by R. Okay, V square by R dt. So that will be, if you put in previous equation of AC power, and here you have to represented your power in terms of voltage, that will be V effective square divided by R. In that case you will get the same equation, okay, for RMS value of voltage. Okay, now let us consider an example that you are having a sinusoidal that is represented by V of t is equal to Vm cos omega t. Here Vm is the amplitude of your sinusoidal voltage and omega t is your angular frequency. Okay, now if you want to find the RMS value of voltage, so put your voltage V of t into this equation, okay, the same equation we are using. So in place of V, we are putting Vm sin omega t, Vm cos omega t, then it will be 1 over T Vm square, the square of this will be Vm square, and cos omega t square will be cos square omega t dt. Okay, this is your final equation. Now from this equation we can get this equation. Let me show you how we can get this. You can just consider this cos square omega t So cos square omega t can be also written as cos omega t multiply by cos omega t. Okay, so this is nothing but cos omega t multiplied by cos omega t will be cos square omega t. Now you know one trigonometric identity, that's 2cc. It means 2 cos a plus b, 2 cos a cos b is equal to cos a plus b minus cos a minus b. Okay, sorry, here it will be plus. So 2cc is equal to c plus c. You may know that. Okay. So here we have the same example, cc. Here 2 is not there. So let us divide this equation by 2. In that case, this 2 will be cancelled, and here it will be divided by 2. So whatever will become this 1 by 2 is nothing but this factor. Okay. Now we have to worry about what is this. So if you do cos a plus b, so here you can see cos a plus b is omega t plus omega t, then it will be cos of 2 omega t. Okay, so apply same rule right here. So c plus c, it will be cos a plus b, that is cos 2 omega t, plus cos a minus b, cos a minus b. So here a is omega t, b is omega t, so a minus b will be 0. So the final answer will be cos of 2 omega t plus cos of 0 will be 1. So here it is cos 2 omega t plus 1. So you can convert this equation Vm square cos square omega t into 1 by 2. This 1 by 2 factor will come into the picture afterward. Okay. So it will be 1 by 2. So 1 by 2 into 1 plus cos 2 omega t into dt. Here Vm square is constant, that is why we can take it outside of integration. Okay. So here you can see the same equation. Now the thing is that whenever we are going to find the integration of a sinusoidal or a cosine function, so the total integration will be 0, because now we know that average of sinusoidal signal is always become 0, because the positive half of the cycle will be cancelled out by the negative half of the cycle. That is why this term will be 0. The only term will present, that is 1. Okay, this 1 by 2 is also constant, that is why it will be outside of the integration. So it will be Vm square divided by 2t integration 0 to t. We don't have to worry about this term, so because that will be 0, so don't consider this. It will be 1 dt, 1 into dt. Now integration of 1 with respect to dt will be t, that is why your next term will be Vm square divided by 2t. Integration of 1 is t and the limit will be 0 and t. Now we have put the t first, in that case t minus 0, it will be t only. So this t and this t will be cancelled out, and finally we'll get the under root of Vm square by 2, and if you take the under root, square root of Vm will be, Vm square will be Vm, and square root of 2 will be root 2. That is what you can see right here. So your V RMS value when your sinusoidal voltage is applied, that is Vm cos omega t, in that case the RMS value is given by V RMS is equal to Vm square divided by square root of 2. Same way you can find for your current when it is given by Im cos omega t, Im divided by square root of 2. So the effective value is nothing but your square root of mean of the square of the periodic signal. Thus the effective value is often known as root mean square value, or the RMS value in short. Okay, because we are doing as per definition we are doing root of mean of the square value of either voltage or current. Okay, So RMS value is nothing but your root of mean of square value. Now here we have to take the note that above relationship holds only for sinusoidal signal. So if your signal is given in form of a sinusoidal, here you can see that your signal is in sinusoidal form, Vm cos omega t. Here also you can see Im cos omega t. So above relation, that is that V RMS is equal to Vm by root 2 and I RMS is equal to Im by root 2. That is only true in case of a sinusoidal signal. If the signal is not sinusoidal, in that case we have to follow the basic definition, that is square root of mean of square theorem. Okay, let's say an example. Here it is time axis. Here your voltage is given in such fashion. Okay, it is 0, here pi, 2 pi, 3 pi. Here you can see that your waveform of input signal, that is V of t, is not sinusoidal. For half of the cycle the value is positive and for half of the cycle the value is 0, and the same will continue. So for one time period we have to take the integration. So if you want to find the VRMS, so what is the definition? That is root of mean of square value, square of, here V square will be there, V square of dt. Okay, here Vm is given in some let's say in positive cycle for 0 to 2 pi. So our time period, total time period will be 0 to 2 pi, and here we can see for 0 to pi the value is positive, and let's say this is given by some 10 sin omega t, and for pi to 2 pi it is 0. Okay, so if you want to find V RMS, in that case it will be 1 over t, that is one period. Here one period is how much? 1 upon 2 pi. Okay, afterward you can see your signal repeat itself. So it is 1 upon 2 pi integration of 0 to, let's say 0 to pi. This nature of the signal is 10 sin omega t. So your will be 10 sin omega t square, okay, V square, plus for pi to 2 pi the value is 0. So it will be you can take the integration for pi to 2 pi, the square of 0 dt, but it will be 0 only, so we don't have to consider that value. Okay, and if you simplify this equation, you just 10 is constant, so take it outside. The sine square omega t will be there, and you take integration, put the limits, and you take the under root, you will have the RMS value of the current, voltage. Okay, so you can directly find the value of RMS voltage and current if and only if your signal is sinusoidal signal using this equation, Vm by root 2 and Im by root 2. In case of non-sinusoidal signal, you have to follow the same procedure. Okay. Now let us consider that that we have discussed in previous lecture, that what is average power, and we have derived the equation of average power when it is given to any system. Okay, so that just remember this equation, that is P is equal to 1 by 2 Vm Im cos theta V minus theta I. Let me just remind you, when voltage signal is given by Vm is equal to Vm sin omega t plus theta V, and Vi is equal to, I is equal to, here it is not Im, I is equal to Im sin omega t plus theta I. Okay, these were your signal of voltage and current, V and I, sinusoidal signal. In that case, we got this expression for average power that is absorbed by a circuit, and that is given by P is equal to 1 by 2 Vm Im cos theta V minus theta I. Here theta V and theta I is nothing but your phase angle of voltage and current. Okay, so that we have derived. You can just check the previous lecture. Okay, now this equation can be rewrite in form of RMS value of voltage and RMS value of current. Here you can see this equation is in the form of a maximum value of voltage and current. So what we can do that this term 1 by 2 can be also written as 1 over root 2 multiplied by 1 over root 2. Okay, this can be 2 can be also written as the multiplication of 2 square root of 2. Okay, so if you multiply root 2 into root 2, it will be 2 only. Okay, now just put this under root 2 in divided by Vm, and same this root 2 under Im. You will get Vm by root 2 Im by root 2 cos theta V minus theta I, and Vm by root 2 is nothing but that we have derived Vrms, and Im by root 2 is Irms cos theta V minus theta I. Now similarly, the average power absorbed by a resistor also can be written as P is equal to 1 by Vm into Im. So just in this equation, whenever the resistive load will be there, in that case your voltage and current will be in phase with each other. That is why the value of theta V and value of theta I will be equal. And if you put theta V is equal to theta I into this equation, it will be 0 and cos of 0 will be 1. That is why your average power absorbed by a resistor will given as P is equal to 1 by 2 Vm into Im. Now also you can write Vm is equal to Im into R, and if you put the value of Vm into this equation, then it will be Im square into R. Okay, now here you can see that it is Im square. It can be written as Im multiplied by Im, and this 2 can be written as 1 upon root 2 multiplied by 1 upon root 2. In that case it will be Irms multiplied by Irms. So the final power also can be represented as Irms square into R. Same way you can put the value of I is equal to V by R into this equation, and you will get the power in terms of RMS value of current and RMS value of voltage. Okay. Now when a sinusoidal voltage or current is specified, and it is often in terms of its maximum value or peak value, or it can be in terms of a RMS value, because the average value of the signal will become 0. So generally we know that your value of sinusoidal voltage and current are specified in terms of either maximum value or in terms of RMS value. We never deal with average value or instantaneous value, because we know that our power industry specify the phasor magnitude also in terms of a RMS value rather than using peak value. So whenever you dealing with a voltage or current in case of a power system or in case of any electrical engineering subject, you will always going to deal with the RMS value or the effective value of voltage and current. Let's say for an example, we are considering that the 230 volt available at every household is the RMS value of voltage from the power company. So we say that we are getting 230 volt, that is RMS value, not the peak value or not the average value of voltage. Also it is convenient in power analysis to express voltage and current in their RMS value rather than using peak value. As far as measuring instrument is concerned, the analog voltmeter and ammeter are such designed to read directly the RMS value of voltage and current respectively. Okay. Now already we have discussed the apparent power and power factor, but let us discuss this term in terms of a RMS value of voltage and current. So we have already derived that the average power absorbed by any circuit and that is excited by a sinusoidal signal is generally expressed in terms of RMS voltage and current as P P is equal to V RMS I RMS cos theta V minus theta I. Now same equation can be also rewritten as P is equal to S cos theta V minus theta I. Here S is nothing but, we can say this quantity S is known as apparent power, and it is generally identified as the product of RMS value of voltage multiplied by the RMS value of current. This is nothing but your apparent power. Okay, apparent power. Now why it is known as apparent power? Because it seems apparent that the power should be the voltage and current product by analogy with DC resistive circuit. So in case of DC, we measured power by just simply multiplying voltage into current, and in previous equation we can see that V RMS multiplied by I RMS is nothing but your apparent power. Okay, now it is generally measured in terms of volt ampere, or we can represent it as V into A, to just distinguish it from the average power or the real power, which is generally measured in volts. Now this volt is a very small units. In electrical engineering we are dealing with kilowatt or megawatt. Same here, we can dealing with kV or MVA. Okay, so it is just to distinguish with average power or real power, we are measuring your apparent power in volt ampere. Okay, so from the previous expression it can be observed that the apparent power need to be multiplied by a factor to compute the real power or average power. So in previous equation, that will be average power can be written as V RMS multiplied by I RMS cos of theta V minus theta I. Okay, these were our last expression. We know that V RMS into I RMS nothing but our apparent power S. So here we can see that the apparent power need to be multiplied by a factor, some factor. This is the factor we are talking about. Then we will get our average power or real power P. Now what is this factor? So this factor is generally known as a power factor, and mathematically it can be represented by, so if you just take S in the denominator of P, you will get the power factor is equal to P divided by S, and mathematically it can be represented by the cosine angle between theta V minus theta I. Here theta V is nothing but your phase angle of voltage, and theta I is nothing but your phase angle of current. So if you know the phase angle of voltage and current, and you know can take the cosine angle between both of them, you will get the power factor. Okay, now let me discuss some range of value of power factor. So the value of power factor generally will between 0 and unity. So if we consider a purely resistive circuit, the voltage and current are in phase with each other because it is the pure resistive circuit. So theta V will be going to equal to theta I. So in that case, cos theta V minus theta I will be 0. So cos of 0 is 1 and your power factor is 1. So this implies that the apparent power is equal to average power. So in this equation you can see that when theta V is equal to theta I, cos of 0 is equal to 1. In that case we can say this P, that is active power or average power, will be equal to your apparent power S. So P and S will be equal when this power factor term will equal to 1. Now for purely reactive load, when your theta V minus theta I is equal to 90 degree, we can say your power factor will be 0 because cos of 90 is equal to 0. So P is equal to your S multiplied by this cos of 90, that is 0. That is why active power, average power will be 0 in case of purely reactive load. It means either your system or load can be capacitive or inductive load, and that is why your average power also becomes 0. Here you can see your average power is 0. Now in between these two extreme cases of a zero power or a zero power factor and unity power factor, it is said to be either can be leading power factor or lagging power factor. So leading power factor means that your current leads the voltage by some degree, and which implies in case of a capacitive load. As far as lagging power factor concerned, your current will lag your voltage by some degree, and that implies that your circuit is having inductive load. Okay, so in case of capacitive circuit or capacitive load, your current will be leading your voltage by some degree. In case of lagging power factor, or when your circuit is inductive kind of nature, your current will lag voltage by some degree. Okay, if it will be purely inductive circuit, in that case current will lag voltage by 90 degree. Or in case of capacitive, that is purely capacitive load, your current will lead voltage by 90 degree. Okay, so that is the case that we have discussed right here. Now the another term that we have to understand whenever we are discussing with RMS value of voltage and current, that is complex power. So let's say your power is given in terms of your voltage multiplied by the current only. So that voltage phasor is represented by Vm, that is amplitude of voltage at an angle of theta V. So this can be also written in the form of sinusoid, that V is equal to Vm cos omega t plus theta V. Here we have represented in terms of a phasor. Here you can see a current also can be represented as I is equal to Im at an angle of theta I. It means in sinusoidal form we can represent I is equal to Im cos omega t plus theta I, and that is the voltage V of t and I of t. So the complex power S absorbed by any AC load is the product of the voltage and complex conjugate of current as follows, and that is S is equal to 1 by 2 VI conjugate. This 2 is nothing but we are representing this voltage and current phasor in terms of RMS value. Here you can see VRMS multiplied by IRMS conjugate. Now why this conjugate term is here? Because already we have dealing with the term that is theta V minus theta I when we are dealing with our average power. Okay, so if you take V conjugate I, in that case that will be theta I minus theta V. Okay, so it will be some difference between the previous discussion and that this discussion that we have. That's why we are taking I conjugate in place of V conjugate. It doesn't make any sense as far as the physical system is concerned. It is only for our understanding and mathematical calculations. Okay, in that case the calculation will be easy if we are taking VI conjugate. So if we put the value of V RMS and I RMS from this equation, it will be V RMS multiplied by RMS at an angle of theta V minus theta I. So we can notice that the magnitude of the complex power S is nothing but if you just convert this equation into rectangular form, then it will be V I RMS multiplied by I RMS cos theta V minus theta I plus j V RMS into I RMS sin theta V minus theta I. So from above equation we can see that this is a real term, and here you can see an imaginary term. So as the magnitude of complex power is the apparent power, so the complex power is also measured in volt ampere. So here you can see in complex power the magnitude, that is V RMS multiplied by R RMS, and it is nothing but your apparent power, and this term is unitless. That is why also complex power is measured in terms of volt ampere, and that is the unit of your apparent power. Okay, here we can see that V RMS into I RMS cos theta V minus theta I plus j V RMS into I RMS sin theta V minus theta I. This term can be also represented as P, and this term also can be represented as Q, because this is nothing but your active power P that we have derived earlier, and this is Q. The unit of P is nothing but watt, and unit of Q is nothing but VAR. Now, same thing that we have were discussing about the complex power being complex quantity, and that can be resolved into real and imaginary part. So this is your active power P, is your reactive power Q. So the real term of P represented the average power that delivered to the load, and it is only the useful power. What is imaginary power, or we can say your reactive power, is represent the energy exchange between the source and the reactive part of the load, that is either your load is capacitive or inductive. In case of a resistive, we can see in case of resistive load, the value of theta V and theta I is equal. So if you put theta V minus theta I into this equation, so here you can see theta V minus theta I is equal to 0 and cos of 0 is 1. That is why only this term will present. Here if you put theta V minus theta I, theta V is equal to 0 or theta V is equal to theta I, the sign 0 will be 0. So this term cannot come into the picture. That is why whenever your only the capacitive and inductive load will be there, in that case this reactive power come into the picture. Okay. So Q is generally measured as volt ampere reactive to distinguish it from the active power that is measured in volts. So as far as the relationship between your complex power, apparent power, reactive power and real power is concerned, with respect to your power factor, it can be easily understood using power triangle. So power triangle is nothing but your correlation of S, P and Q with respect to theta. So from here we can see that S is nothing but your active power P plus J Q. Also, if you want to find the power factor, that is cos theta is equal to P, that is your active power divided by apparent power S. Okay. Same way also you can represent S as P under root of P square plus Q square. So if you want to find the value of S, just use the Pythagoras theorem and you will get P square plus Q square. So power triangle is easiest way to deal with active power, reactive power and apparent power and power factor. So with this we are closing our today's lecture. In next lecture we are going to deal with some another topic from sinusoidal steady state analysis. Okay, we are going to deal with mutual inductance and the inductive reactance and ideal transformer. Okay, so see you in next lecture. Thank you so much.